So here is the convolutional neural network's basic concept compared to ANN, right? If you remember, in the ANN we use the so-called fully connected, right? Fully connected relation between your input and output, right? So you have input, so-called predictors, maybe x1, x2, x3, x4, so on and so forth. This is what we call the predictor, right? And then we use the hidden layer. You can assume whatever the number you want as the neurons. And the fully connected means all the previous neurons will be connected to all the following neurons. So that's what we say fully connected, right? Then eventually you have your output layer. So this is the input, this is the hidden. And then we have the output layer. Just use this one. So this is your output layer. Right? We have learned this from the ANN. And here, the predictors you select, which is a characteristic from your observation or from your specimens, right? We know that they have some meaning based on your observations, based on the target you want to predict. For example, if you want to predict the compressive strengths of your concrete specimen, right? Then the predictor maybe becomes like the Young's modules, right? Like the dimensions of your specimen, right? The cement ratio, right? Something like that. So they have specific meaning, physical meanings, real world meanings, and they are potentially has something to do with your predictions. Right? There's some relationship we want to know. But maybe they are nonlinear relationships. So that's why you use the ANN. In ANN, all these connections, they are the linear combinations. But when you have a lot of combinations for those linear relationships, you can actually describe the nonlinear relationship. But the key point is, these predictors are selected by you, by your professional judgment, and they are actually well organized. Right? They are well organized. But things are going to be different if we look at images. Right? For the image case, suppose that we're looking at the grayscale images, okay? No color, just grayscale, black and white. So for black and white, if you have some concept, those pixels is a range from 0 to 256. Right? And then they are distributed on your images without any specific rule. Right? Maybe here is 5, is 0, 1, 7, whatever, 6, 250. So there is no specific rule or the choice of this pixel number on an images. They just naturally form out. And then when we look at them, look at the images, visually you can realize, hey, there's a cat or there's a dog. So the relationship between those visualizations to our concept, to our recognitions of an item is unknown. It's not well organized. You don't know the specific relation. So this kind of the data is so-called non-well organized. So you can imagine that the predictors here selected by you, but the predictors here describing images somehow selected by maybe by God. So it's like naturally distributed. You don't know why they distributed like that, but somehow when you look at it, hey, you know that's just a cat or a dog. Okay? So the key point here, again, in the ANN, we try to introduce this weight and the bias, right? Or the intercept. To know this linear relationship. Similarly, we want to use some weights and the bias here to capture those features, to capture those unseen relationships. For example, maybe this combinations, or this combination, or this combinations, so on and so forth. Okay? So that's the key difference for CNN, and the key difference between it to ANN, artificial neural network. But conceptually it's the same. You still try to use the weights and the bias and then connect it to your neurons. But here the input neurons is not well organized. The input predictors is just like images. So it's not well organized. So that's the key difference. But you'll see that eventually when you have multiple so-called convolutional neurons, convolutional layer, the kernel, and then we will again use the fully connected layers after those CNN layers. So the CNN, not just including CNN itself, they actually combine convolutional layers and ANN layers, or the fully connected layers. Okay? So that's why we start from the ANN. It's more easier compared to the CNN. So these are the concepts about the convolutional kernel, how they can extract the information from the images, especially from a lower dimension to a higher dimension. If you decompose your images, as I have shown you here, so numerically in the computer, these are what we can know from the images, right? Just like a matrix with a lot of numbers within all the elements. And for our brain, we kind of looking at the final output from a combination of these image pixels, right? But if you want to realize the underlying structures or underlying relationship, then the CNN can help you to decompose these images. Like when you started using the kernel, first you look at the lower level of the features, such as curve, right? Some node, some curve, some edge, even a dot, right? A circle. This is the lower level features. And then when you use a further kernel, you'll try to extract based on the previous knowledge, based on the previous feature you selected. You try to extend those informations. And then if you look at this higher level of the features, all these curves and the line and the circle with the black dot combined together look like an eye, right? Or a mouse, or a ear, the tails. That's a higher level of the feature. So you can imagine that we look at this item, visually we understand that's a cat. But numerically, for the computers, it needs to understand like layer by layers, from the lower level of the layers with the lower level of the features, and then combine it together to a higher level of features, and then realize that, hey, that's so-called an eye, or ear, or mouse, or whatever the feature inside that image. Okay? So once you have all these features from lower to the higher, and then we realize that, hey, that's a cat. I'm sorry, this one is a tiger. Well, tiger is part of the cat, I guess. Belongs to the cat. Okay, so that's the concept about the CNN. Now let's look at this one. So I think this is a very typical images if you search CNN on Google. It tells you the architectures or the structures about the CNN layers, the CNN models. Basically, it combines a lot of convolutional layers. So every convolutional layer was trying to extract the features. So maybe in the first couple of layers, CNN layers, with the kernels, they are trying to extract the lower dimensional features. And then so on and so forth, they try to extract like the middle dimensional and then the higher dimensional features. And eventually, all this combination together, we use the fully connected layers again. Because the fully connected layers eventually can lead all your combinations to the target we want to predict. Right? You want to do the classifications, or you want to do maybe the regressions. So eventually, you still need a fully connected layers. Right. So again, this is the images. You don't need to be fine about the brand of these cars. Just a car. And you have a lot of background information. So the user convolutional layers try to extract the main characteristic for this car. And then, usually we use the value. Do you remember the value? We have used that in ANN, right? Which is a function that tries to introduce the nonlinearity, right? The value function suppose the output is h, the value function of x is, if x greater than 0, then you output x. If x is smaller than 0, then you output 0. Right? Do you remember? That's the value functions. This is the value. Right? So it tries to emphasize those more important features from the input, from the previous neurons. So here, when you have a lot of value after all these neurons, after the convolutions, it's trying to introduce some nonlinearity when you have a lot of value. That's what we call the activation functions, right? Okay. So usually you have convolutional layers and a value, and then maybe another convolutional layer and value. And the original image size may be, like 256 by 256. That's kind of a normal image size. Then we don't want to have such a huge matrix, which actually will become tensor when we think about the 3 different channels, RGB, 3 different colors. So try to reduce that dimension. But in the same time, we try to keep those important informations. And that's where usually we'll use so-called the pooling. So like, for example, originally you have these images 256 by 256, and maybe you can use some pooling layers to small it, to reduce the size. Maybe only 128 by 128. Right? So after kind of the contractions of the information, eventually, those informations you learn will be connected to so-called fully connected layers. So this is the typical architectures of the CNN model. Of course, for more advanced model, we have other techniques to maybe highlight the nonlinearities. So we'll talk about that. But typically, the architectures, if you want to build up from scratch, it's like convolutional layers, with the value activation, with the pooling. So this is one unit of the CNN, convolutional value and pooling. And then you have another unit, convolutional value and pooling, convolutional value and pooling. So you have multiple units combined together, and that's the CNN model. So now let's take a look at the so-called kernels, how they actually extract the information from your input images. Now, suppose we have an images. Let's just look at the grayscale. So it's like a 2-dimensional. And let's just use this example. A, B, C, G, H, I. So this is your images at grayscale. Okay? Then we try to introduce this convolutional kernel or the filter, so that it can extract the information from the images. And then let's assume that in this kernel, conceptually the same as previous ANN, you need to introduce some weights and the bias, right? So let's assume that the weights in your kernel is alpha, beta, gamma, and delta. Okay? And then you can think about using this kernel to scan over the images to extract information. So the first round extractions use this kernel based on the size, which is a 2x2. So when you map back, and when you map this kernel back to your original features, only use these 2x2 dimensions to extract the information from your input images. And this kind of extraction, again, is the same as here. They are just doing the linear combinations. So once you use this, it will become alpha A plus beta B plus gamma C plus, gamma B plus delta E. Right? So that's the first, you can imagine that's the first neurons you combine. Here, from the previous ANN example, you have predictors, well-organized predictors, right? And then you have a weights and a bias that combine all these predictors to these neurons, right? So which is the same here. You have a weights and a bias combined to previous predictors to a new neurons. Okay? So that's the concept. But this is just one of the neurons. We are now moving on to next scanning, which is here. You shift your kernel to the following elements of the images. So again, doing the linear combinations. So it's alpha B plus beta C plus gamma E plus delta F. So you can imagine that's another neurons combined from the previous predictors. Okay? So conceptually, they are the same, but mathematically, you are doing from one-dimensional to two-dimensional. Okay? Right. And then we can keep on working on the following extractions. Again, use this and also use this. So then this one is alpha E plus beta E plus gamma G plus delta H. And the last one becomes alpha E plus beta F plus gamma H plus delta. Okay, so that's the output after your kernel filtering. Right, so conceptually, we have talked about the CNN. Your input images, a three-dimensional channel, different size of the elements, which is similar to the ANN, but ANN is more like a well-organized predictors, but in CNN it is not well-organized. So that's why we use the kernel to extract the information. And we use the kernel, you can also use the stripe to skip or keep the information. And you can also use the patterns to keep your dimensions so that you can work on those stripe of the extraction of the information. So that's the concept. That's what I want to show you today. Pretty much just concept about CNN.